Welcome everybody to Colloquium number 3. Today our speaker is Brett Stevens, and he's going to be talking about scheduling the video game Olympics using geometry.
Lights on, please. Okay, so every year at the University of Mary Washington, which sounds like a very British title, like it might be Queen Mary or something like that, but it's actually Washington, George Washington's wife. They have a video game Olympics. And the number of participants they have every year is not always the same, but generally they have a target and an underlying structure that they're after. Right? They have 64 participants. And they booked 8 rooms for 8 one-hour periods. So you can think about this schedule as a big grid.
It comes in mirror.
They come in.
The writing's backwards on the video.
Oh, are you serious? How does that happen?
So, can you do some mirror writing?
Okay, I'll try and do mirror writing.
That's not mirror on the little screen. No, that's the one over there.
So we make a big 8 by 8 grid.
Maybe there's a mirror setting. You can fix your hair.
And these are the rounds. There's 8 rounds. And I have 8 rooms. Now in each room there's some video game console with apparently 8 controllers. I don't know how you do that, but I probably can be done with Wi-Fi. And basically we would take the name of each participant and write them into a square, right? So if Sam is in room 1 in round 1, so you can never be in the same room again, because we want to get Sam's proficiency at 8 different games. So maybe in round 2, we put Sam in room 2, and there, and then maybe we do something strange, like in round 4, we put him in room 5. Sam. Sam. I'm sure I've done something wrong.
Okay, one more vertical line.
Sam, Sam. And we do that for 64 people, and we have a schedule. And at the very least, no matter how we did that, as long as there were 8 people in every room, then every player would have the same number of competitors at every game. Every player or participant would play every game. And if we had some means for adding up the scores at the end, we could do that. Now, that's pretty good in and of itself. But we're not able to control for at least one kind of important piece of information. And that is whether or not when Sam and David play a game, Sam tends to do well, or David tends to do poorly, because of something to do with their relationship, that pair of relationships. So typically in tournament design, we would like to have the option, not the option, in the schedule we would like to know for sure that given any pair of people, there's one time at least when those 2 pair of people play against each other, right? So if David brings out the worst in Sam, that's part of Sam, right? And if David brings out the best, that's also part of it. But on the other hand, we don't want to overly punish Sam and have Sam, if this brings out the worst, and David is playing with Sam a lot, we're making this not a fair tournament for Sam. Or vice versa, if it brings out the best, it's not fair for everyone else. So we'd like to see as many pairs together as we possibly could, and we don't want too many pairs repeated. That's kind of our goal. Now, we should, at the beginning, try to get a sense of how well we actually can expect that we can do. So how many pairs are there? You can just say 64 choose 2.
Yeah, 64 choose 2.
There's 64 choose 2 pairs, and in every room, how many pairs are there?
Oh, wait, 8 choose 2.
8 choose 2. Well, I should say in every room round. And how many room rounds are there? There's 64 room rounds. Okay, so 64 times 2 is 32 times 63. I already did the division by 2. And this is 4 times 7 times 64. And let me make this 32, and that 4 an 8. And we see that this is 56 times 32, and there are 63 times 32 pairs. So the pigeonhole principle tells me that no matter what I do, there are going to be pairs of people who never see each other, right? Because I have that many pairs actually happening in the tournament, but there are this many pairs of people. So some of them will not happen. So we can't expect to get a perfect tournament. So I want to start by looking at a structure that would give us some means of making a tournament if some of these numbers were a little bit different. And of course, I'm not really interested only in 8 and 64. I'm interested in n squared and n rooms and n 1-hour periods. So I want to solve this in general. So I want to talk about an almost solution that breaks this part of the rules, but it has some nice things about it, because every other solution that we're likely to get to is going to be built from that solution. Okay, any questions? Okay. I can't tell you how to win at Mario, because I don't know. Okay, so suppose that n was a prime power. That's nice because we will have a finite field. Okay? So I'm going to start doing examples where things are very simple. In case you don't know what a finite field is, I'm going to do n is equal to 3. Okay? And I'm going to tell you what the finite field is. So the finite field of order 3, which I write as a kind of a thickened F with a 3 in it, it has 3 numbers in it, 0, 1, and 2. And I'm going to tell you how they add and multiply. For the most part, they add and multiply exactly the way that you'd expect them to. Does anyone not know finite fields here? Or does everyone know them?
Well, we all know modular arithmetic.
Well, you all know, okay, perfect. Then I didn't know if there were some people who wouldn't. So let's just say that As long as it's not a prime power, it's really just modular arithmetic. Great. And the important thing is, though, that I have both plus and multiplication, which means that I can solve general linear equations, right? Like, where do two lines intersect? Things like that. Okay, so the affine plane is a geometrical object, but I'm going to do it over Z mod 3. So this is just the Cartesian plane, and instead of the real numbers, we do Z mod 3. So what are the points? Well, it's just the Cartesian product of Z mod 3 with itself. And there are lines which are really just things like, they're sets of points. They're the set of points x comma y, where y is equal to mx plus b for some choice of m and b in Z mod 3. And you can really literally think of those as slopes and y-intercepts if you want to. And it's easy to actually draw those lines. Do I have all of them, by the way? What am I missing?
You need the x equals such and such.
Yeah, so there's actually these other ones, which are the points x, y for y in Z mod 3, where I choose an x value. Those are the vertical lines. So I can draw them, and I chose 3 because it actually gives me a nice drawing. So there's my slope 0 lines. Here's my infinite slope lines. Is that pink actually kind of showing up? And here's a slope 1 line. And another slope 1 line would be this one here, but it also includes this point. So things aren't totally straight. And here's another slope 1 line, which includes this point, if you calculate out the y mx plus b. And I need one more color. We'll try orange. That might look like pink, though. I don't know. There's a slope, line of slope -1, which is also slope 2. Right? So slopes actually do really live inside the modular arithmetic. And here's its other lines like that. There we go. Okay, now, this has a lot of nice properties that we're very, very familiar with, because it's the same properties that happen in the Cartesian plane. For every line and every point not on the line, there's a unique line which is disjoint from the given line and goes through the point. That's just the parallel postulate. You had a question?
Well, I'm just wondering, I guess all the lines have to go through all the points, like you can't have a slope 1/2.
No. Well, you can actually have slope 1/2, because what's 1/2 in Z mod 3?
I'm not sure.
So 1/2 would be the thing which, when multiplied by 2, gives me 1.
Oh, okay.
So what is it?
Oh, okay, then it's, what's 2 to get 1? Is it?
2.
No, 2 times 2 would give you.
2 times 2 is 4, and I take the remainder when I divide by 3.
Oh, that is 1, okay.
And that's 1. So let's actually
slope
see,
1/2
though.
is slope 2?
Slope 1/2 is slope 2.
Okay.
And we can actually literally see that, right? So slope 2 would be
Be through those.
this and that, right? 1 over 2 up. And indeed, this and that are on an orange line, which I said earlier was slope 2.
Oh.
Now what's slope 1/2? 2 across, 1 up. The way I drew it just doesn't emphasize that, right? If I'd drawn this line like this, that would emphasize the slope 1/2ness.
What is that?
If I'd drawn it like this, I would emphasize the slope 2ness. But I drew it like this to emphasize the slope -1ness. But those are all the same thing, right? And it's all there. So we've got, and the lines of the same slope are disjoint from each other. They're parallel, right? That's what parallel would mean in this very discrete setting, that the lines share no points in common. And I have 4 different parallel classes for my 4 different kinds of lines, 3 different possible slopes, and my vertical lines. Okay, so I can make a schedule from this, and let me show you how. Well, one way to do it would be to say, well, I've got, it would be to put the grid right on top of this thing, right? So rooms and rounds. So I have n rounds, which will be my columns, and I have n rooms, which will be my rows, as it were. And every person gets assigned a line. And that's your schedule. So how many people do I have? Well, how many lines in each parallel class? 3. And how many parallel classes? I said that earlier.
4.
So 12. Now, in general, I should finish this sentence, scheduled for 1 person. So what is that? That's n times n plus 1 people. Well, that's not what I said, right? I wanted n squared people. But that's okay, because what's wrong with this schedule? Why will this not work as a schedule? So if I am the first yellow line, so here I am in round 1, here I am in round 2, here I am in round 3. So there's a problem with that, but it's a fairly innocent problem. It just means that I've had to play World of Warcraft 3 times, right? I mean, things could be worse, right? It's actually feasible for me to do that, right? But, you know, what about pink 1? In the first round, pink 1 has to play Warcraft and Mario Brothers and Mario Kart, all in that hour. That's just impossible.
I know people who could do it.
There probably are people, but, you know, whether we can find n of them, I'm not sure. Okay, so I have to get rid of the vertical lines. Minus vertical lines is n squared. So I have a schedule. It features n squared people organized into n rounds and n rooms with n people in each round room pair. It looks great. It does, however, violate one of the things that I really wanted, and that is that I wanted to be able to test any particular person at any game. But it's pretty close. I only have 3 people who don't get to play all the games, right? And as n gets big, that's a vanishing fraction of the number of players. But I want to enforce my conditions. I am going to require that we have every schedule hit every round and every room as it goes. If I wanted to get that out of this, I'd have to erase my yellow lines so to keep every player playing every game, we would have to subtract the horizontal lines. And now we would have n times n minus 1 players. And if we were satisfied with that solution, we'd be done. Because once I erase these yellow lines, I really do have n rounds, n rooms. I have too few people, but maybe some people dropped out at the last minute. And I have every person playing every single possible game. And that's a feasible solution if we have fewer people. But I'm interested in kind of exploring what would happen if my requirements are rigid. I cannot let go of the fact that there have to be n squared people, n rooms, and n rounds. So what does that constraint force on me? And we're going to be building our solutions from that kind of system. But I first want to actually do some counting that will give us the right measures to tell us whether we're doing a good job or a bad job. Okay? Okay, and I want to define some variables, so just give me a second. Remember what my variables names are. Okay. So, I'm going to start to formalize the problem. I've got X, which is a set of n squared participants, and I'm going to look at this set. So for x, little x, and little y in my big set, I'm going to consider I forgot one thing that we need. We also need the schedule. N squared participants, and Bij is participants in round I, room J. There we go. So note that when I say that I'm going to be strictly enforcing my requirements, I need that Bij and Bij prime, so same round, different rooms, has to be disjoint. And the same thing same room, different rounds, has to be disjoint. So I'm requiring that. Now, if we go back to our picture, we had these sort of parallel classes of lines. And within each parallel class, things were disjoint. This is kind of like having two separate parallel classes of something, right? I have the parallel classes given to me by the rounds, right? Those B's in the vertical strips of B's. are all disjoint, but it's also true in the columns, and that was never true there. I had only one way of decomposing that into kind of parallel classes. So this is a requirement. And now, for x and y, I'm going to define lambda xy to be the size of this set. It's the number of those b's, and I'm not going to draw the subscripts all the time, that x and y are both in. Right? So that's the number of times that x and y see each other. And that comes back to the thing which I really wanted to actually count. Repetitions. Okay? How many pairs miss each other? That would be a lambda 0 pair. How many pairs see each other 3 times? That would be a pair such that lambda xy was 3. And then I'm going to let ni equal the size of this other set. Ni are the number of pairs which see each other exactly I times. Okay, so this is essentially my formalization of the whole structure. And I should ask you whether you have any questions. Yeah.
Just the subscripts on B.
Yeah.
Bij there. So we say that Bij, just like Bij, is that prime?
So the prime here is on the j. The i's are the same and the j's are primed. So I've got the same round,
So
different rooms.
Okay.
I'm saying you can't have someone in 2 different rooms on the same round. And then this, so that's just physically impossible, except for Colin's friends.
Yeah.
And this one says, okay, you know, I don't want the same person playing the same game in 2 different rounds. That's feasible that we could have that, but I don't want it, so I forbid it. And so the prime is on the I here, which is the round. 2 rounds, same room. Other questions? Okay. So I'm now going to introduce to you a technique that we use in combinatorics all the time to try and get more information out of our system, and it's called double counting. So I'm going to count a set I, which just consists of all the possible pairs. Now I count it in 2 ways. Now it's kind of weird to count this in 2 ways because maybe I can do this without. So I'm not sure I can. I know the number of pairs, right? N squared choose 2 is the number of pairs. These should be unordered pairs. I'm abusing my brackets like crazy. Okay, but I'm now going to count that in a different way. I'm going to count it by looking at each block and seeing how many things I get. Actually, it'll be more clear on the next one, I think. This is just no one can see themselves more than n times because I'm only in n different rooms. So it should be clear that the number of pairs is also just the sum of the ni's, because every pair has to land in one of these sets. It has some I, and I'm just adding up the sizes of those sets, which are all disjoint. So that's not double. That is double counting, but it's not crazy double counting. Here's another one. I'm now going to count this set. And I can count this in 2 different ways. So I can start by counting it from the point perspective. So I'm going to count it all over all pairs of points, and then I'm going to count the number of blocks that that pair appears in. And now if I count it from the block perspective, how many blocks are there? What's a block? It's the set of people who are in a room round. So how many do I have? Okay, I've got n squared blocks. Now, there, so once I've chosen a block, that's how many choices I have for blocks. Once I've chosen a block, how many pairs are there for me to count in that block?
You choose two. Or N choose.
And choose 2. And now I can rewrite this I'm just going to break that sum up into a bunch of smaller sums depending on the I, the lambda, for that xy. Right? So I have a sum of xy such that lambda xy equals 0 plus xy such that lambda xy is 1 and finally xy such that lambda xy is equal to n. Right? I could fail to see someone, I could see them once, twice, 3 times, but I can never see them more than n times. So I've just split up my sum depending on what the lambda value of any particular pair is. Well, do you see how I can simplify that now? If in this sum, I know that I'm only looking at xy such that lambda xy is 0, I can plug that in here. And this is just 1, and this is just n. Well, now these are sums over constants. So all that really matters is what?
The number of things you sum.
The number of things I'm summing. How many things am I summing here?
Ni. Or N.
Not ni.
N0.
And 0. So it's n0 times 0, and n1 times 1, and nn times n. So this whole thing is really just this. I know now 2 pieces of information. The sum of my ni's is this thing, and the sum of I is this thing. I want to gain one more piece of information, and it looks like this talk will mostly be about double counting and not about solutions as much. Let's see where I can get to. Okay. I want to know something about this. I squared ni, that sum. I'd like to know exactly what it is, but it's going to turn out that I can't, right? Because this is going to be something that's going to vary. How can I get this information? How can I get I squared ni? Any ideas? I'm going to count this set. When I count it by points, here's what happens. Right? So I'm going to look at every possible pair, and then I'm going to see how many pairs of blocks, let's say they're distinct. How many pairs of blocks can I find where both of these pairs appear? What would that be? So I've got an xy. I know how many blocks that pair appears on, lambda xy. How many ways do I have of choosing two of those? Lambda xy choose 2. Now, I can do the same kind of manipulation. I can break this sum up by what the lambda values are, 0, 1, 2, 3, all the way up to n. And this then becomes, I choose 2, and I. Which, when I simplify it, right, that's equal to, well, it's 1/2 I squared ni plus 1/2 the sum of I and I. And my eraser's over here. And I know what this is, because I calculated it here and just erased it. So I can get rid of this part and then multiply by 2. So that's only one way of counting, though. I've got to count the other way. Now, I can look at every possible pair of blocks, but I don't know what the size of their intersection is. Will they have a pair, or will there only be one point in one, or will they be disjoint? I don't know. That's part of what we're actually going to see when we construct it. But what I do know comes back to the pigeonhole principle one more time. There's B00. N people are in there in round 0. Where do those people have to go in round 2?
Somewhere else.
Somewhere else. How many somewhere else's are there?
7.
N minus 1.
N minus 1.
I'm putting n people in n minus 1 boxes. There has to be at least one repetition. And that's for every possible room round I can consider. And there's one pair of those people will see each other again here. But one pair of these people will also see each other again in round 2, and 3, and 4, and 5, and 6, and 7. So that gives me just the edge of a count. I know there are guaranteed to be a certain number of pairs of blocks I can pick where they must have an x and a y in common. And that allows me to work out the following. It gives me a lower bound on what this thing has to be.
Sorry, why do they have to? Why does a pair have to stay together in the next round?
Because I've got 8 people, I've got n people in there. Those n people can't be in that room again.
Right.
So they go
yeah.
somewhere to n minus 1 rooms. I
Right,
have to have at least a pair.
I forgot that being in the same block didn't mean they were playing each other.
Yeah, so it's pigeonhole principle again. But I'm able to now, I know the following. The two ones where I could get exact answers previously and And then I get a lower bound on that final piece of information. And now I have a way of determining how good my solutions are. They're as good as I come close to meeting this bound. So that's going to be my measure. What's the sum of I squared and I? Okay, and I've got enough time to at least show you one solution, which will meet the bound. Okay, so let me do a quick calculation. If I subtract this from this, I get I squared minus I, which is I times I minus 1, and I get that that must be greater than or equal to this minus that, which is this. Okay? Now notice here that when I is 0 or 1, this term isn't there. So this is equal to the sum from I equals 2 to n of that same thing. That, because I know I is always less than or equal to n, I can make an upper bound where I replace the i's by n's, and this I can just calculate out. Well, I can. I don't know exactly what that is, but I can pull these constants out. And now I can cancel them on the upper and the lower bounds. And I get this. There are at least n pairs who see each other at least 2 times. So here's the question. Can I find a solution which matches that? That would be the fewest number of people seeing each other more than twice, more than once. That would be good in my measure. Okay? So here it is. Where am I going to draw it? I'm going to draw it here. And go back to my affine plane. Right? That's some grid of points. And those points will be the room round pairs. And the people will be the lines. Okay? But I gotta get n squared, and I can't have 2 people playing in the same room in different rounds. So that was the problem I had earlier when I went to the affine geometry. I wonder how loud this is on the streaming video when I drink. Okay. So remember, I've got my yellow horizontal lines, and I had, I don't even remember my colors anymore, some color, pink vertical lines, and I had to get rid of all of those. But I also had, like, say, lines of slope 1. Now, when things are prime powers and not primes, it doesn't look so pretty, right? Your slopes are now polynomial values. But all the algebra works out because you can still always add and multiply and subtract and divide by something non-zero. So let me put one more color in of, say, lines of a different slope. Now, of course, when we're not in Z mod 3, 2 is not the same as minus 1 is not the same as 1/2. So things will change up that way, right? Okay, so here's the construction. I erase the pink lines. I have to erase the pink lines. They're not even feasible, except to a few people. I'm glad I didn't draw too many. And I get rid of the horizontal lines because I don't want someone to be playing the same game all the time. Okay. Now, I simply pick a slope, slope 2, and I put a second person in there. I'll do the cross-hatching so you can tell them apart. So I did have n squared plus n lines. I deleted the vertical ones and I had n squared lines. I deleted the horizontal ones and I now have n squared minus n lines, but I've just doubled n of them. So I have n squared lines again. Got the right number of people. I've got the right number of rooms, the right number of rounds. Nobody is in the same room more than once. How do I know that? Well, if someone was in the same room more than once, say here and here, that's 2 points. There used to be a line between those 2 points. If there was some other line, that would be saying that when I solve an equation of the intersection of 2 lines over a field, I get more than one answer. And that can't possibly happen because division is unique. Right? That's where things go wrong if you don't have prime powers. So that doesn't happen. So that guarantees the condition we want. Now what's wrong with this solution?
The overlap is always between the same 2 people.
It is, right? Dave and I see each other every single time we play, and Dave just intimidates me, man. And I just can't shoot goblins when Dave's there.
Well, why don't you just stagger you and Dave at different starting points, and then you and Dave just won't ever see each other?
Then you'll see someone else every round.
Yeah, it'll be, if I shift this line, it will line up with one of the other orange ones.
Well, each line is a person moving through their games, through those points.
Yeah.
So, and each point is a person starting?
No, the points are the room rounds. People are lines.
Right, and when you get to the end, it wraps around.
It wraps around, exactly.
Okay, so if 2 people start on the same line at different spots, then they'd just follow each other. They wouldn't run into the same.
A person is a line. I mean, they can't. You don't start in a line in the same spot. This line says in round 0 you're here.
Oh.
So even if it's the same line, they can't start in 2 different places.
Okay.
They're both here in round 0. I keep switching where 0 is. Sorry.
That's all right.
Now you could do something like this. Instead of picking one slope and duplicating each point, each line in that slope, I could pick, like, say, 1 orange and 1 green and 1 blue. But remember what's true of 2 lines of opposite slope in the Cartesian plane. What happens? They have to intersect. So suppose I doubled this orange line and that green one. Here, well, okay, I used to have n plus 1 lines through there. And I got rid of the vertical and the horizontal one, so I have n minus 1 lines. Now I've duplicated the orange one through there, I'm at n, and the green one through there, I'm at n plus 1. So I can't ever duplicate lines with different slope. Otherwise, I'll get too many people in one room at one time. And I'm stuck. So I have to pick. If I'm going to still only have n people in each room in each round, I have to pick a whole set of parallel lines. And that's terrible, right? If these two players have a bad effect on each other.
It seems like there are a lot more ways
Oh, there's tons of ways.
to put people in different rooms in different rounds, and here
Yes.
we're considering some very regular ways to do it.
Yeah. So this is, in fact, the only way that I know that you can meet that bound on the sum of I squared ni. Everything else I found is not as good.
Really?
Yeah. So somehow, meeting that one particular measure of goodness gives me something which is very bad in a different particular way. Okay, so that's no good. What are we going to do instead?
That in itself is a really staggering fact.
I know. Okay. Here's the thing that I like least about that solution. I like least about that solution that I had ni greater than 0 for some I greater than or equal to 3. I know some repetition is unavoidable. There are going to be a pair of people, Dave and Sam, who see each other at least twice. Let's limit it to twice. They can't see each other more than twice. So I'm going to do the following. I'm going to impose this condition. Ni is equal to 0 for I greater than or equal to 3. No one sees each other more than twice. Okay, now all of my equations simplify to the following. I have a typo in my notes. And n2 is at least this. So if all the ni's go away, for I bigger than 3, my 3 equations become this. And now I can ask myself, can I meet this bound? It's not the same bound anymore. In fact, in a very natural way, it's twice as bad. I have twice as many literal pairs who see each other more than once. And it's unavoidable. But can I do that? Well, okay, let's think about what we actually had to have. I need to know for certain. I'm going to add in n more line-like objects. Okay? That's just some set of n points that hits every room and round exactly once. So I cannot have two pairs like this. Right? You can't go through 2 points that look like that. Now, what do we call, you have to stretch yourself a little bit here, just because the metaphor's weird. What do we call a set of points, x comma y, that contains every x, and for every x there's only one y?
A bijection.
A function. Okay, so I'm looking for some function. Oh, good, right? I mean, I can write down lots of functions. I need it to do one more thing. I need it to not be cut in two places by a horizontal line.
So it is a bijection.
So it's a bijection.
Or decreasing function.
And here's where I can go and take advantage of the finiteness, okay? So I gotta describe this kind of quickly, but this is the essence of projective geometry. A projective geometry, projective plane, you build it from the affine plane in the following way. For every slope, you add one new point. So here's my new point of infinite slope. Here's a point of 0 slope. And here's a point of slope 1, and so on. Now you can do this over the real numbers as well. And I extend every slope 0 line to include this point. So they all meet now, but they meet over here at infinity. Hand wave. And then I throw this new line in. Now, if I could come up with a function that meets any line in at most 2 points, and I could ensure that it contained this point and this point, then it couldn't be cut twice by any vertical or any horizontal. Because if it got twice by these two, this would be a third. And I said this was some kind of function or set of points that a line only hit twice. And this is why you put things into projective geometries. Because you get properties like this. I know tons of these functions. Namely, any quadratic has the property that even when you extend it to the projective plane, you make these lines longer, you add these new points, any line hits it in at most 2 points. So I'm just looking for functions that are quadratics that in the projective plane go through this. Well, it turns out that that's really easy, and I want n-disjoint ones. Here they are. So these are my new lines, right? So I'll call them CI, CC. They're just parabolas. You can check, and I don't have time to do the details, that this particular parabola always goes through that point in the projective plane, which means it can't be on 2 points that are on a horizontal line together. And they're all disjoint because they're just shifts of each other. And then I throw these points away, and I'm back down here. So I've essentially done something like this. I have added some new lines, which I need some color for, but one of them goes through 0, 0. It goes through 1, 1. It goes through 2, 4. Now, of course, since things wrap around, it starts to very quickly not look like a parabola, right? 3, 9, and then 4 is, down here somewhere, or something like that. So it starts out looking like a parabola. And then I just take the vertical shifts of them. And that's n new lines. And because they come from quadratics, any other line meets them in at most 2 points. Now, that gave me 2 consequences, which were important. Because one of those lines was here, and it was a point, one of those points was here, that it was a point on all 0 slope lines, that guarantees that this never happens. I never repeat 2 rooms, different rounds, same person. But all the other lines in here also don't intersect this quadratic in more than 2 points. Which means that if you consider any person who was one of these lines before, and any one of these new people who's a quadratic, they meet at most twice. So ni is 0 for I greater than or equal to 3. And it's exactly what we want, and it meets this inequality. Now, I don't know that that's the only solution that meets this inequality. Maybe there's others. So we impose a condition which gets rid of the thing we really didn't like. We get a new set of constraints, and we can construct something that meets that. The problem being that the number of pairs of people who see each other more than once has doubled. Now, I'll do the rest just really quick. This kind of solution has two different kinds of people, line people and parabola people. Okay? The other solution had two different kinds of people, non-duplicated line people and duplicated line people. I could impose the constraint that all the people are the same somehow. What that really means is the number of, if I'm one person, the number of people I see 0 times, 1 time, 2 times, 3 times, and 4 times should be the same as the number of times you see someone 0 times, 1 times, 2 times. And I don't know what to do in that situation except in one case. And that's where not only do I insist that that's true, but I insist that there's an automorphism group of the entire structure that takes any one person to any other person and all the blocks. And in that case, when I work that out, I get that, which means it's 3 times as bad in terms of the total number of pairs of people who see each other more than once as my original solution. But somehow it's much nicer because it's so highly symmetric. And that's, at the moment, all I really know.